Alright, so today's going to be our introduction to geometry. And in high school, geometry is going to look very different than geometry that you've seen before. So my goal over the next couple weeks is to just kind of give you a sample of what that's going to look like, what types of work you're going to do. In a way, it's not going to feel like math, and it's definitely going to feel very different from algebra. In reality, this is actually probably more like the math that actual mathematicians or the people working in that field are doing in the real world. And everything that you've done up until now is just kind of like building up your background knowledge to get ready for that. Right? What mathematicians do is they look for patterns. They try to prove things to each other. And they try to make new discoveries about numbers, patterns, and geometry, right? Spatial representations. Okay? So in geometry, the first thing we're going to talk about is some of kind of the notation that is used, right? So you'll see things like, you see a lot of diagrams in geometry. If I have a geometric diagram, maybe it looks like this. This is a really common one, at least at the beginning of geometry.
Should we draw that?
Yep, you can draw this. So what is this diagram saying?
It's not.
Well, what it's saying is we've got a line segment here and a line segment here, and then we've got four angles that are formed by those two line segments.
Yeah.
Okay. So this angle right here, in geometry, we would call angle 1, and we'd write it like that. Right? So this is angle 1. This is angle 2. This is angle 3, and this is angle 4. An important thing to realize about geometry, though, is that an angle is just an angle, right? It's not a number. So if we wanted to talk about how big angle 1, angle 2, angle 3, or angle 4 is, we would talk about the measure of that angle.
Oh.
So this notation here is used to label or name angles, right? Whereas this notation is used to measure, right? Or quantify angles. And there's some important reasons for that. Okay? When we're talking about different angles, like over here, if we're just labeling them or naming them, we use something called equivalency in geometry. So for example, I might say that I know that angle 1 is equivalent to angle 3. Right? And I would write that like this. Angle 1 is equivalent to angle 3.
But wouldn't you have to say that the measure of angle 1 is equivalent?
So equivalency is used with equivalent, right? This is used when we're actually just naming the angles. If I wanted to say that their measure is equal, I would say it like this. The measure of angle 1 is equal to the measure of angle 3. And these mean basically the same things. This is actually, we could call this a rule of geometry, but we know, right, equivalent angles have equal measurements. This is an important statement. It's an important, you could even call it a postulate or a definition. And these types of statements are going to be something that's really common in geometry. I'm going to call this the definition of equivalent angles. The definition of equivalent angles is that equivalent angles have equal measurements. Okay? And this is how geometry is going to go. You're going to state things that at first might seem really obvious or really simple, or like this, it's just defining what this little thing means. Right? But you're going to build on those to develop more and more complex rules, which you'll call postulates or theorems, depending on whether you prove them. Okay? So this is our first definition. It's the definition of equivalent angles. I want to talk about a couple other things in here, in this diagram. First thing I want to talk about is linear pairs. So in this diagram, we have linear pairs in the angles 1 and 2. So angle 1 and angle 2 are a linear pair because together they form a straight line. Right?
Oh, yeah.
Angle 1 is also a linear pair with angle 4 because together they form this straight line. Right? Angle 2 is a linear pair with angle 3. And angle 3 is a linear pair also with angle 4. Now what do you think is true about linear pairs? No matter what. Okay. They create a line. What do you know about lines? And I want you to think about angles and degrees.
Well, they're all 180 degrees.
Yeah. Right? So if two angles are a linear pair, that means their measurements have to add up to 180 degrees, right?
That means you could like for
Right? So this is going to really be the definition of linear pairs. Linear pairs are angles that form a line together, right? And linear pairs are what in geometry we call supplementary. Supplementary means they add up to 180 degrees. So linear pairs are supplementary. And a supplementary, what supplementary means is that the measurements add up to 180 degrees. So now I'm going to draw a diagram. And we're going to kind of do the first steps of like a proof. I want you to prove. I want you to prove that this diagram is not possible. We'll call this 1. This is 2. This is 3. We'll call this 4. So can you prove to me that this diagram is not possible? And you might see it right away, but what I want you to do is to really walk through each step of what you're noticing. Okay, what do you notice?
Me or Jack?
Silas, go ahead.
Okay. Well, one thing I noticed is that 2 and 3 should be a linear pair, but they aren't supplementary because 120 and 50 isn't 180.
Okay. Jack, did you
And
want to say
also 1 and 4 are add up to 200. Or
190?
yeah.
So they also don't add up to 1.
Yeah, so it's kind of like.
So how could we kind of write that out? Like, what would we write?
You would write the equal sign without.
Yeah, like the do not equal.
Okay.
Like
So-
angle 1 plus angle 4 do not equal.
So like the measure of angle 1 plus the measure of angle 4.
There's not equal.
Yeah, wouldn't it be the equal sign with the copy?
Yeah, couldn't you?
We kind of want to prove that this does not equal 180
Yeah.
degrees. Kind of like that?
Yeah,
Yeah.
but then do we have to go deeper and like prove this?
Yeah, so how could we actually show this now?
You could say.
You could get the actual measures, like.
Yeah.
So the measurements
like
are actually
60
given,
plus
right?
130.
So
Yeah.
60 degrees plus 130 degrees does not equal 180 degrees. Now, in what's called a two-column proof, for each step that we do, we're going to write a reason. Now, the reason for this is just that this is given, right? This is given to us in the diagram.
Wait, so what do we do?
So we're doing kind of like a two-column proof, where we're saying, this is what I'm noticing, and this is the reason that I can notice that. What's kind of our justification for this step? Like, what are we trying to say here?
Would that be given to you?
No?
Wait, what are we?
Like, where does this whole idea come from? That measure,
linear.
like,
Linear
yeah,
pairs?
right? So here we could kind of say linear
Pairs have to equal.
pairs are supplementary. Right?
Yeah.
That's kind of a statement that we had made before. But in this case, what we're showing is that they're not supplementary.
Which means that it doesn't work.
Right, which means that it doesn't really work.
Wouldn't be like if those lines are sort of equal, like everything, and like what the degrees are. So would that also be something that doesn't work?
Could
Like you know how you said that like the definition of equivalent angles, those angles are equivalent.
okay.
Would that be?
Yeah, should any of them be equivalent?
Yeah.
Yeah, they all should.
No.
Yeah.
Well, like this doesn't have to be equal to this, right? I mean, I could draw a diagram where those are very clearly not equivalent, right?
Oh,
Like
what
this
is supposed
doesn't
to be
have to be
equivalent
equal to that,
is
right?
1 and 3 and 2 and 4 are supposed to be equivalent.
Oh.
Like 3 should
And
be
they're all
60
like
and 4 should be 1.
So,
And then it would actually work.
so what we're kind of noticing is that if I label 1, 2, 3, 4 around like that, angles 1 and 3
Should be equivalent.
should pretty much always be equivalent. Could we prove that that's true?
Yeah.
How would we prove it?
I don't know how.
Like,
well,
And this
one
is
way
the
of-
key with a two-column proof, is that
You could say like
we're going to think through our proof first before we start to actually write down them.
Could I say like all equivalent angles have to have equal measurements?
Okay, so we're going to have to appeal to the definition of what equivalent means. So then how could we show that these should have equal measurements?
Well, because then they don't add up to 180 if they aren't equivalent. But how would you write that?
Like these should add up to 180?
No, but I mean, if 1 and 3 aren't equivalent, and 2 and 4 aren't equivalent, then
Let's just focus. So this is kind of a good tip for geometry in general, right? Or making a proof in general. Let's just focus on 1 and 3. Okay, just proving those are equivalent. Because maybe it's also true that 2 and 4 are equivalent,
But we're not focusing.
but we can't.
Okay.
We probably aren't going to be able to prove both of them at the same time. So let's just focus on proving that 1 and 3 should be equivalent. And how would we do that?
According to the definition of equivalent.
Well, because
But how are we going to show that these should be equal? How do you know that they should be equal?
Because it looks like it.
Okay, it looks like it.
Maybe because it all adds up to 360.
Okay, they all have to add up to 360. But that... Well, like, based on what you guys have said, I mean, I could have them be really close, right? Like 79 and 80.
Don't they create a right angle? So, like, okay, those two, 1 and 3, don't they create a right angle to equal 180 if they're supplementary? If they're linear pairs?
Well, 1 and 3 aren't a linear pair.
Oh.
Right?
You can see they don't, if you combine those two angles, it's like 1 and 4, 4 and 3, 3 and 2, 2 and 1.
But maybe we can use that to help us show that 1 and 3 would have to be equal.
Because they're not linear pairs?
Maybe. They're not linear pairs, but like, let's think about this. If this is angle 1 and this is angle 3, let's say I knew that angle 2 was 30 degrees.
And then they have to be.
What would angle 1 be?
It has to make 180 on both sides.
Yeah, so
And then split it
These
down.
are both linear pairs with angle 2, right?
Yeah.
They both have to be linear pairs with angle 2.
But there's only one number that can make a linear pair.
And there can only be one number that can make a linear pair with a given other number. So if we can show in our proof that angle 1 and 2 are linear pairs, and so are 2 and 3, then we should be able to show that 1 and 3 are equal.
Yeah. So it would be 1.
So we want to start out, right? We want to start out with something like, this. Angle 1 and angle 2 are supplementary.
What? Yeah, but you have to prove it.
Right? Angle 1 and angle 2 are supplementary. And we know this because they're linear pairs. And linear pairs are supplementary. So we're just trying to walk someone else through our thinking. The other thing that we know is that angle 2 and angle 3 are supplementary. For the same reason, so I'm just going to put ditto marks. So then, if angle 1 and angle 2 are supplementary, then the measure of angle 1 plus the measure of angle 2 should equal 180 degrees. Or we can just say 180. Why?
They're supplementary.
Yeah, that's like the definition of supplementary angles. Right? That's what supplementary means. We can just call that the definition of supplementary angles. And for the same reason, we know that the measure of angle 2 plus the measure of angle 3 equal 180. What could I do next? I almost have here, like, you could think about this being a system of equations. This is kind of like a system of equations. Would you agree that if one thing equals 180 and another thing equals 180, then this thing has to equal this thing? Does anyone remember what that's called? We actually talked about it.
It's like
Starts with a T.
Transitive property.
Yeah, the transitive property says that if this is equal to 180, and so is this, then these things have to be equal. The measurement of angle 1 plus the measurement of angle 2 has to equal the measurement of angle 2 plus the measurement of angle 3. We're almost there, actually. How could I get this to say that the measurement of angle 1 equals the measurement of angle 2?
Well, you can subtract the
Yeah.
angle 2.
Can't I subtract the measurement of angle 2 from both sides? That's called, this is called the subtraction property of equality. So for all of algebra, we've been doing this, but we never actually talked about why we could do it. Right? The subtraction property of equality says that I can subtract something from both sides of an equal statement, it will still be equal. So when I do that, I get the measure of angle 1 equals the measure of angle 3.
Oh, wow.
We're not actually done yet, though.
Yeah, what's the best?
Because what we want to show is not that just the measurements are equal. We actually want to show that angle 1 is equivalent to angle 3.
Why do you draw
And
a
that's
squiggly line?
our definition, because this means equivalent.
Oh, doesn't it mean
That's the definition of equivalence. So we've just kind of shown that angle 1 is equivalent to angle 3. No matter what the numbers are, these two should be equal. And this actually has a name. This is called
the property?
the vertical angle theorem. People call it different things, but we'll call it the vertical angle theorem. Why do you think we would call these vertical angles? They're vertical to each other.
Was the guy who found it last name Vertical?
So we just kind of walked through our first proof, right? More or less, using this two-column method. Where over here we're kind of doing the math, although it doesn't really feel like any math that we've done.
We really don't.
But it is. And over here we're giving our justifications. All right?